Good morning, everybody, and welcome to this mini symposium on fictitious domain methods and application. Before we start, I would like to thank Pedro and Frederick for inviting us to organize this mini symposium. This mini symposium has been organized by Professor Rank from Munich and Enrique Nadal and myself, both of us from the Polytechnical University of Valencia. The mini symposium is split in 2 sessions with a total of 10 presentations. So we think that given the special circumstances that we are going through, having these 10 presentations in the mini symposium clearly shows that there is an increasing interest of scientists in fictitious domain methods. For this particular session, we are going to have this 5 presentation we have in the screen, and I encourage you all to use the chat to ask the questions. Please indicate the name of the presenter you are addressing the question to. And then we are going to start with the first talk, comparison of safe derivatives using CAD-FEM for ill-posed Bernoulli-free boundary problems. Thank you.
Hello, everyone. This is Cui Yu, and first of all, thanks for watching this video. In this video, I will talk about shape optimization methods for ill-posed Bernoulli problem using CAD-FEM. And this is a joint work with Professor Eric Berman and Professor Mats Larsson. We study the inverse interior type Bernoulli free boundary problems. The problem was to find the domain with Lipschitz boundary such that the following conditions are satisfied. Note that 2 boundaries we have here. Gamma fix is the outer fixed boundary, and gamma 0 is the unknown closed boundary inside the domain. I would like to give you one example. In this example domain, gamma fix is the outer boundary or is the boundary of the square domain. And the gamma 0, the free boundary, is the boundary of the ellipse. And the domain omega is then the domain of the square domain minus the ellipse. We need a few assumptions here. So the first one is the distance of gamma fix and gamma 0 is bigger than a positive constant a. And another assumption we need to have is to assume there is a unique solution gamma 0 determined by the given data. Okay, we rephrase the original problem into an optimization problem. First, we denote capital O by the admissible set of the domains. For every given domain omega in the admissible set, we will define the cost functional, which is half times the L2 norm square of the difference between GD and U of omega, where U of omega satisfies this Poisson type well-posed PDE problem. So the original problem now transferred into this constrained PDE constrained minimization problem. Find omega in the admissible set such that it is the minimization of the cost functional. Since it is a constrained PDE, we can embed the constraint into the Lagrange multiplier and then taking the Gateau derivative with respect to W and V, we could find the corresponding primal and dual solution denoted by U and P here. U and P needs to solve this again 2 Poisson type PDE problem, and numerically we will use cut finite element method to solve this. And then the original optimization problem now became the unconstrained optimization problem, which to find omega, which is the minimizer of this now Lagrange multiplier, but with U and P being the primal and dual solution. For the rest, in order to solve for this solution omega, we will use the iterative method of the gradient descent type. And now I would like to summarize the algorithm of that we use. First, we will choose a reasonable initial guess for the free boundary gamma 0, and we represent it as a level set function. And then we will solve for the primal and dual solutions based for the Lagrange multiplier. And then based on the gradient descent method, we will solve for the steepest descent gradient or velocity. And based on that steepest descent gradient or velocity, we will solve for the level set of the new free boundary. And based on the new level set or updated level set, we will get the update the free boundary, and we continue the iterative procedure until we get the true solution or the stopping criteria is satisfied. So due to time limit, I will stop here. If you are interested, you are more than welcome to check our manuscript posted on archive over here. And also, you can also check the longer version of this video afterwards. Thanks again for your attention.
All right. Let's move to the second presentation, which is efficient simulation of crack propagation in complex geometries using a phase field model on the finite cell method.
Hello everyone, my name is Lisa Hook and I want to give you a short overview of my talk, Efficient Simulation of Crack Propagation in Complex Geometries using a phase field model and the finite cell method. I will talk about how a phase field model can be combined with an embedded domain technique and adaptive refinement, and which additional ingredients are necessary towards an efficient simulation of real-world crack scenarios. As a motivation, let's consider this core sample taken out of 3 to 5 kilometers depth somewhere in South Bavaria. On the right, we see a computational model based on the CT scan of the same core sample. If we want to perform a phase field analysis on this, we face several challenges. First, we have a complex geometry. To avoid a complex mesh creation, we use an embedded domain technique, the finite cell method, which is based on an implicit representation of the geometry. Secondly, we have small length scales. We need to resolve the pores inside the geometry, but also the length scale parameter of the phase field. Here, an adaptive refinement technique can help to save computational time and memory. A third point, and the focus of today's talk, is the determination of realistic material parameters. Let's start with a quick introduction on phase field modeling. The basic idea here is that instead of directly representing the crack and thus a discontinuity, we approximate the crack with a continuous Gala field, the phase field S. Now we can see that our crack is essentially smeared out, and the phase field variable is 0 on the crack and takes the value of 1 in the undamaged region. Crack propagation follows directly from the solution of a partial differential equation. Failure in rock is often governed by mixed mode fractures, and usually the resistance to mode 2 fracture, so shear failure, is significantly higher than the resistance to tensile cracks. In the classic phase field approach, we only have one fracture toughness GC. That's why we used the mixed mode formulation by Zhang, where we split the total crack driving force into a part associated to mode 1 fracture and a part associated to mode 2 fracture, and we also introduced two different fracture toughnesses GC. The question is now, how can we determine the fracture toughness GC2? As there is little data available in literature, we decided to perform the experiments ourselves. We used the double-edge notch Brazilian disc tests proposed by Barami, where a Brazilian disc specimen containing 2 notches of fixed length is diametrically compressed at an angle alpha. 2 wooden plates are attached to the top and the bottom of the specimen to induce the load. The experimental results are summarized in the table on the right. As we can see from experiments, we obtain a K1 to K2 ratio of 4.73 for the Solnhofen stone and of 2.78 for the Braundorfer Dolo stone, which is in good agreement with literature. Here we can see the simulation setup, where we initially refine towards the notches where we expect the cracks to initiate. We compute L0 based on the material parameters for each type of rock and end up with 2 different length scales here. To compare the simulation results obtained for the Solnhofen limestone, let's first have a look at the crack pattern observed in the experiments. We can see that 2 tensile wing cracks starts to form, and then shear failure occurs abruptly between the 2 notches. Now, looking at the simulation results, we can see that we obtain a very similar crack pattern. We get the 2 tensile wing cracks, and then the shear band starts to form in the center and shear failure occurs. If we now look at the load displacement curves computed in the simulation, we can see that also the critical failure load we obtain matches very closely to the experimental values. To summarize, we've combined a phase-fit approach for brittle fracture with the finite cell method and adaptive refinement. We have determined GC2 for 2 types of rock using double-edged notch Brazilian disc experiments and successfully calibrated a phase-fit model for mixed-mode fracture. The next step will be to compute more complex 3-dimensional crack scenarios. Thank you for your attention, and I'm happy to answer any questions.
All right, thank you. We go now to the third presentation, so 5 FEM, the finite element method on domains defined by level sets.
I am Alexis Luzinski from Université de Franche-Comté at Besançon, France. I am going to tell you about a new fictitious domain method, FIFEM, on which we have been working with Michel Dupré and Vanessa Lieras. We are in the world of finite elements. We are thinking about Poisson equation with Dirichlet-Neumann boundary conditions, but we don't want these fitted meshes. Rather, we embed our physical domain on a simple background mesh, and we devise some tricks to take into account the boundary conditions. Of course, we are not the first ones to do it. Classical approaches of this time, fictitious domain method, go back to 60s and 70s. The solution is extended there from the physical domain to the computational one, and then boundary conditions are taken into account by penalization or Lagrange multipliers. This gives easy to implement methods, but they are of bad accuracy. We cannot expect better than square root of h error in h1 norm, and this is due to the poor quality of the extension of the solution from the physical domain to the computational one. This extension is indeed not smooth. We have now more recent, more elaborate, more accurate methods like XFEM or CutFEM, where the background mesh is still used to set up finite element approximation. But no extension is supposed for the solution outside of the physical domain. So with Lagrange multiplying or Nietzsche approach with appropriate stabilization, we get indeed optimal accuracy. But At the same time, the methods are difficult to implement because of these cut cells. So indeed, the weak formulation is set up on the physical domain. So it means that we should compute the integrals over the cut portions of the mesh cells. So here comes our idea, FIFM, in which we hope to get the best of the two worlds. So we extend the solution outside the physical domain omega as an old fictitious domain. In the same time, we can do it with optimal accuracy as in XFEM, CutFEM. The method is based on the level set function phi, hence the name phi-fm. Phi is simply something negative inside the physical domain omega, so vanishing on its boundary gamma. And the starting point of our method is to provide a weak formulation of the problem, allowing for a smooth extension of the solution up to the boundary of the computational domain omega h. And we also include the level set phi in the weak formulation. So here is how it works for Poisson problem with directly boundary conditions. We don't work directly with a primarily unknown u. Rather, we introduce the new unknown w, and the ansatz u equals phi times w. So u automatically vanishes on gamma since phi is 0 there. With this, we can forget about the boundary conditions on gamma and to set up the weak formulation on the extended domain omega h. So this formulation is not good in the PDE world, but with appropriate stabilization terms, it provides indeed a valid finite element scheme. And we can prove the optimal error estimate in H1 norm, so using finite elements of any degree k. Numerical results suggest optimal accuracy also in L2 norm, and we have also a good control on the condition number of the rigidity matrix. So numerical results indeed indicate the optimal convergence in both norms with P1, P2, P3 finite elements. And here is a graph to indicate that stabilization is really necessary. We can do the same with Newman boundary conditions, although everything is more complicated, but both theoretical and experimental evidence is there. And here are my conclusions. Thank you to your attention.
Thank you. We move now to the fourth presentation. Don't you forget to launch your questions to the chat. The fourth presentation is processes optimization using contact formulation in the Cartesian grid finite element method, CFEM. Thank you.
Thank you very much for watching our presentation about processes optimization using contact formulation in the Cartesian grid finite element method. As you may know, topology optimization algorithms try to find the optimal material distribution over a given domain based on the minimization of a loss function and the satisfaction of a set of constraints. The stress shielding effect reduces the bone density due to the change of typical stresses when replacing the original bone by an implant, and also there is risk of aseptic rejection. The motivation of this work is to use topology optimization to design implants that reduce the stress shielding effect. The outline I'm going to follow. Let's begin with the image-based CGFM. Simulating the processes problem in a standard finite element method, the first step is to gather the information of the medical image of the bone and the geometric model of the implant. Then, the next step is to get a segmentation of the bone based on the medical image. And finally, you obtain the finite element model by means of the geometric models previously shown. In image-based CGFEM, we avoid the segmentation step in order to get directly the finite element representation based on the medical image. The first step is to embed the medical image in an SC2 mesh domain. In CGFEM, this domain is a cube. Then we obtain the element discretization of the medical image, and in order to integrate properly the stiffness matrix, for instance, we give each of the integration points the information of the material properties stored in each of the boxes of the original medical image. If inside of an element there exists an excessive variation of the gray level, we are able to refine this element until we reach an adequate distribution of gray level. As this is a edge-adaptive mesh refinement technique, this may be applied locally, which in this case, this implies that we get an implicit representation of the boundary of the medical image, as it usually has higher density of elements. The prosthesis problem I show you in this slide is defined by the medical image of the mandible and the geometric model of the implant screw, along with some boundary conditions, which in this example we constrain selected degrees of freedom to avoid solid body motion in the image and uniform pressure on the top surface of the implant. Then with this information we define properly the prosthesis problem as it is shown in the right side of the slide. I will continue with an overview of the structural topology optimization and a 3D example. The objective of structural topology optimization is to find the optimal material distribution of a structural component that minimizes the compliance in this case, which measures the strain energy, and also satisfies a set of structural constraints as maximal stresses or a given volume reduction. In this work, we base on the SIM method. Here I show you different representation of the optimal material distribution in the implant of the prosthesis problem. To continue, I overview or propose to the stress shielding topology optimization and show a 2D. In this case, the objectives are to find the optimal topology based on structural criteria, the optimal topology that minimizes the stress shielding effect, and a topology that maintains the prescribed volume reduction. The idea behind the proposed loss functional is to obtain similar state of energy in the implant and in a prescribed area of interest of the bone. Here I show you some numerical examples of the heat processes depending on the value of the weighting factors. To finalize, I gather some remarks. CGFEM allows to simulate efficiently the implant bone behavior and the contact between the bone and the implant. The developed structural topology optimization technique works with the implant inserting a bone. We propose a methodology to design implants that reduce the stress shielding effect. And about further works, we would like to check the validity of the functional proposed for the stress shielding reduction, and also we would like to join this proposed methodology to the bone remodeling effect.
All right, let's move now to the last presentation. It's a two-level topology optimization for high-definition material structures under the Cartesian grid finite element method framework.
I'm going to present this work that has been done in collaboration with Rafael Merli, José Albelda, and Juan José Ródenas that tries to define a methodology to obtain high-definition topology optimization optimized structures. Well, topology optimization tries to find a material distribution optimal in a certain manner, which minimizing a certain functional, normally the compliance. Then what we obtain is the stiffer structure as possible for a given quantity of material. And normally we use the SIMP method. Well, when I want to obtain the topology optimization, the optimal topology of a given structure, we use the standard SIMP method. However, in some situations, we want to split the structure into cells and then optimize the cells. Then what's happened is that the structural continuity between cells is not difficult, is difficult to guarantee. But well, the good thing is that it's possible to make a parallel computation of the topology optimization of each one of the cells. So the objective of this work is to develop a cell-based topology optimization process able to build continuous structure by splitting the full structure in cells. Well, which is the idea? First, I perform the finite element analysis of the full structure. Then I can obtain what are the nodal forces in each one of the elements of the big structure. Then, since the forces are in a global equilibrium, it is possible to obtain or to know which are the forces applied to each one of the elements. Then, from this, it's possible to obtain the equivalent forces that are in equilibrium with the neighbor elements, side by side. Okay, this is done thanks to the Maxwell diagram that was introduced by Ladevez and Maunder some years ago. This idea comes from the from the error estimators, and we use these ideas here in topology optimization now. Then, when we have already unequilibrated traction fields over the boundary of the elements that comes from the finite element solution, then we can define a topology optimization problem with an equilibrated traction field into each one of the elements of the macro problem. Then we run the standard optimization problem, the SIMP for example, and we obtain a topological optimized structure into each one of the elements or cells of the big structure. Since this traction field is equilibrated with the neighbor element, then the structural continuity is smoothly guaranteed. And I can run in parallel each one of the optimization problems for each one of the elements of the big structure. Well, now I'm going to present this problem, and I have an L-shaped domain, and the procedure starts as follows. First, I run a standard optimization process in the macro level, not to define a structure, just to give a distribution of the material quantity into each one of the cells or elements. Then I perform the Maxwell diagram and obtain a traction field equilibrated into each one of the cells or elements. Then I run the optimization process in each one of the cells for the given quantity of material assigned into each one of the elements, and I obtain this structure that, as you can appreciate, tries to be a continuous structure between the elements, and this allows to build each one of the cells, and when I glue each one of the cells, there is structural continuity between the cells or the elements in this case. Thank you very much for your attention.
All right, so we finished with the presentations, and I encourage you to ask questions through the chat. I have a few of them, and I also have some questions myself. I would like first to go to ask some questions to the first speaker. There's a
Juania, I'm not sure if the speaker is here.
Oh.
If he or she is, please write to us in the chat, then we can give you the permission to speak. But Juania, I don't think we have the speaker here at the moment.
Yeah. Okay, then we move to the second speaker. Alexei Lothinsky is asking Lisa. Lisa is around, I suppose.
And Lisa is here.
Hello, Lisa.
Yes, I'm here. Hello. Can you hear me?
Thanks.
Perfect.
Yeah, there's a question from Alexei Lothinsky. Could you briefly present the finite cell method and its relation with XFEM, please?
Yes, I will share my screen if that's possible.
Okay.
Okay. So basically, the idea behind FCM is that we have our physical domain, which we embed into a geometrically larger domain of simple shape, which we can easily mesh. And our actual geometry we will recover during the integration with the help of an indicator function alpha, which is close to 0 in our fictitious domain and is 1 in our physical domain. So basically, if we look then at the weak form of our couple problem, we can see that the contributions of our fictitious domain are multiplied with our indicator function alpha, which is close to 0 and thereby eliminated. And what concerns the combination with XFEM, so I'm not aware of a contribution which combines XFEM and the finite cell method. I know that there is work on local enrichment, but this concerns material interfaces. But yeah, we did not look into that direction. So we are just working with the phase field method.
Okay, thank you very much. There is another question from Frederic Legol to Lisa as well. How do you model the initial crack? By a real crack in the domain or already with a phase field model? And also, what is the rationale behind the choice?
So basically in the phase field method, crack initiation is included in the problem. So for this geometry, there's no need for an initial crack. This would basically also put some assumptions on our problem. And in this case, the crack just initiates then close to the notches.
Oh, Lisa, you have plenty of questions. There's plenty of questions for you. There's another question from Yanis. He's asking, my understanding might be wrong, but it looked like the parameter I0 was tuning the width of the level set function. Could you give some insights on this parameter, on how this parameter is chosen, and how the stability of the simulation is affected by it?
Okay, yes, so basically the parameter L0 determines the width of the crack, and there are some ongoing discussions about the interpretation of this parameter, because naturally it's a numerical parameter which should be chosen very small, so that basically our phase field solution in the limit L0 to 0 approximates our actually discrete crack. But there has also been some research on interpreting the phase field parameter as a material parameter. And because the phase field parameter is 0 determines basically the peak stress at which the crack initiates. So there was a formula which I showed. Maybe I can
please
quickly share it again. So basically we see here, and it's a publication by Chane, 2018, that we can compute a zero based on our material parameter and the tensile strength of the material. And by that, we basically match the peak stress of our material.
All right. I also have a question for you. But I really like the idea of connecting the phase field model with the finite cell method. It's quite interesting. And have you already developed the phase field model for 3D? Are you working on this already?
Yes, so we have also validated our phase field method in combination with FCM in 3D, basically on this problem here, where we have this graphite specimen with an inclined notch at different angles. And basically the angle then induces a mixed mode crack. And we have also managed to reproduce both the crack pattern. So we see here how the crack evolves, as well as the load displacement curves. There's a publication on that where we propose this as a benchmark problem, which you can look up.
Yeah, very good. You also use mass refinement. How is the mass refinement driven? Is it in terms of an error estimator, or do you simply refine where the phase field is not one? How does it work?
Yes, exactly. So it's basically based on the solution of the phase field. So we define a threshold value, usually around 0.5, and then refine the corresponding elements.
All right. There is another question from Frederick Legol. Does the phase field model that you use distinguish between compression and traction? Several variants have been proposed in the literature. Can you comment on this?
Yes, so we have a tension compression split. So the model we are using by Zhang is based on the Mir split. So basically we are only using, this is a spectral split of the strains, and only the positive parts of the strains then contribute to crack propagation. And basically the model of Zhang is based on this split, and then further splits only the tensile parts in the tensile part, which is on the one hand then related to tensile or 2 mode 1 and 2 mode 2 fracture.
Okay. I think we are going to move to the third presentation. Is Alexei Latinsky around?
Yes,
Yeah.
I hear you.
Yeah, thank you.
Can even show me.
Yeah, I have a couple of questions. Did you find any problem in elements only having a small portion of its area into the domain? Or are the stabilization terms solving this problem?
The stabilization terms are exactly there to have a robust formulation. So both numerically and theoretically, we prove that we are robust with respect to any with respect to the manner that the interface or the boundary cuts the cells.
Yeah, and could you comment a bit about the stabilization terms that you're using?
Yeah, if I can. So I don't know if I can. I guess share the screen.
Yeah, thank you.
Here. Okay, normally you see my presentation. Well, a little bit more slides. Sorry. Yeah, here. So you see here all the stabilization terms. So basically, the idea for stabilization is the same as in CAT-FEM, so this cost penalty. So we penalize the jumps over all the edges or faces which are cut by the by gamma, by interface, and also this edge on these edges. But there is one technical modification. So in original CAT-FEM cost penalty, usually if you use finite elements of degree k, then you should penalize the derivatives of all the orders up to k. Here you see, and what we do, we penalize only the first order derivatives, and we add a kind of least squares. It's also grad div stabilization. So essentially we reimpose the equation. The equation is delta u is equal to f. Our u is phi times w. So we reimpose it in a least squares way only on these cut cells. And with some appropriate pre-multiplier factor. And so combination of cost penalty, or this reduced cost penalty for only first order derivatives with this kind of least squares gives us the necessary control over all the derivatives. So the nice thing is here that stabilization works for whatever finite elements at the cost of this reduced cost penalty. Now you have all the details.
Okay. Thank you very much. And one more question. I understand that you do not need any special subdomain integration techniques to consider the boundary, but then you will need to properly sample the element with integration points. How do you deal with this? Do you use many of them, or?
Yes, so very good question, thanks. Indeed, in theory, yeah, the theory is done for exact integration. So yes, we don't have integration on the cut portions, so we don't integrate here. We integrate on the whole triangle, but we should integrate it exactly. So, and it's kind of cumbersome because so. Let us take the less order finite element. So my variable is, say, in P1 linear finite elements. By I multiplied with P1 approximation to level set. So I should, okay, in all the terms, I should deal with effectively P2 finite elements. So in order to integrate exactly, I should normally reduce the order of integration. Okay, that's in theory, but in practice, we have tried. We can kind of forget about this trick of multiplication and use the simplest numerical quadrature, which typically for P1, which will be just one quadrature point, and this still works. This is on for the moment. We have only numerical evidence for this, no theory, but it seems to work. So,
okay. Yes, there's another question from Jerome Walkers to you. Will this work for nonlinear problems?
I hope so, but for the moment, okay, there is a list of ongoing work. So yeah, unfortunately, we had time and energy to deal only with simple, real linear problems. So apart from Poisson, we now have stocks and stocks with rigid particles in it, but it's really stocks, not Navier stocks in a creeping regime. But yeah, in principle, the technology is not limited to linear case.
Okay. There are no more questions for you, so I'm going to go to the next presentation.
Thank you.
So thank you. Thank you.
Juanjo, we have one Enrique with us, but we don't know if that's the right person though.
Excuse me, say it again.
We have one Enrique in the meeting, but we don't know if that's the correct
Enrique.
Enrique.
Yeah. He's
His name is Enrique Nadal, and he joined before, but
yes. Yes. Yeah, but first I have another question for David Munoz.
Yeah.
David, could you comment a bit on the criterion used to optimize the implant and minimize the stress shielding?
Yeah,
you have little time to explain it in the presentation.
I hope you all can hear me.
Yeah. Now we can hear you now. Yes.
Yeah. Okay. Thank you, Juanjo, for your question. Let's see. The minimization of the functional proposed in this work to minimize the stress shielding tries to generate an energy state equivalent in the prosthesis to the one existing in a prescribed area of interest of the bone. And the aim or the goal of this strategy is to represent a situation as similar as possible to when there was not an implant there. And by doing so, we thought that the stimulus of the bone is kind of the most appropriate to avoid bone density reduction. And that's what we are looking for.
All right. Thank you.
You're welcome.
Thank you, David. And there is a last question for Enrique Nadal from Moitinho. Enrique, Moitinho is asking, inside the cells, the lines with material correspond to stress trajectories? Enrique?
Hello, yeah, now I have the microphone ready. Well, good morning. I hope they follow the stress trajectories. We didn't check it at the moment. Now what we're imposing are a linear traction fields on the boundary of the cells, and that is the topology that we obtain using a standard topology optimization procedure. And normally the topology optimization try to make, in general, bars that are normally traction or compression. Since this is the most optimal topology, so they should be the direction of the tractions at the end. But this is not in a soft manner only, not in a strong manner, of course.
All right. Thank you, Enrique.
Welcome.
I wonder if there is any other question. No. So we have 10 minutes left. But if there are no more questions, I think we will close the session. No more questions. And all right then. Thank you very much to all the presenters and all the attendees to this session, and I hope to see you again tomorrow in our next session and in person in the next ATMOS conference. Thank you very much for attending.